Gas and Turbine Engines by Garrett Corwin. So first we're going to get into the turbine engine theory and explain how the fuel is converted into thrust in the engine. So fuel or air starts by coming in through the air inlet, directed into the compressor section where it is compressed. This compressed air is then moved into the combustion chamber where fuel is misted and ignited with the air, and this gas is combusted and moved in through the compressor turbine, and this chemical energy is used to rotate this compressor turbine, create rotational energy, and then the exhaust gases come out through the opposite end of the engine and expelled away from all of the sections. Some gas laws that are important to consider in gas and turbine engines. So the first one is Newton's second law, force equals mass times acceleration. So the mass, which is the air and the fuel, multiplied by the acceleration, which is basically the airflow leaving the engine, will result in the output force, which is thrust. Also, for the other gas laws, Newton's third law, for every action, there is an opposite and equal reaction. So as air is directed behind the aircraft, thrust will be produced, moving the aircraft in the forward motion. Energy cannot be destroyed. It can only be changed into different forms. Once there's a certain amount of mass put into a system, it will be conserved and only changed. Charles's law, when there is a constant pressure, the temperature and volume will be in direct correlation with each other. So for an example of this, as air is heated, volume of the air will increase. As air is cooled, the volume will also decrease. So there's a direct correlation between the two. Now we're going to move into the types of gas and turbine engines that are commonly seen. The first that we're going to talk about is the turboprop. And this engine's exhaust gases don't generally contain enough energy to act as thrust itself coming out of the exhaust. Almost all of the engine's power is used to drive the propeller. So you can see the air comes in through the inlet, moves through the compressor, is combusted, and turns the turbine section, which is geared to the front propeller. The exhaust gases come out the back, which aren't used as propulsion, and the main power is used to turn the turboprop. You can see this is used here in the King Air, which we have at UND. The next engine is the turboshaft. The turboshaft is optimized to produce shaft power rather than any thrust coming from the exhaust. Turboshaft engines are similar to turbojets with the additional turbine expansion to extract heat energy from the exhaust, and it's converted to turn into shaft power. So here's the compressor section again, just like we saw in the turboprop, and it's combusted and it turns the internal turbine, which goes into the gearbox and creates shaft power. This can be seen in the T625 helicopter here. The next engine is going to be ramjet. So ramjet is a form of air-breathing jet engine that uses forward motion to compress incoming air. It has no axial compressors or centrifugal compressors because ramjets cannot produce any thrust at zero airspeed, so they can't move from a standstill. A ramjet-powered vehicle requires assisted takeoffs to get to where at a speed where it can begin to produce thrust. And so you can see here in the SR-71 Blackbird, they're most efficient at supersonic speeds, even up to usually around like Mach 3. You can see here the inlet into the fuel injector system, and the thrust is completely from the exhaust gases um, force behind the aircraft. Now we're going to talk about the difference between the low bypass and high bypass engines. Bypass is referring to the amount of airflow either directed into the engine and combustion chamber or around the combustion chamber. For a low bypass engine, this means that there is no bypass of air around the combustion chamber. So this is used mostly by military combat aircraft um, that basically sacrifice the fuel economy in exchange for high power to weight ratios, supersonic performance, and the ability to use afterburners. So when you take all of the air into the combustion, it's being 100% used um, in the exhaust to create some sort of power acceleration. Contrary to that is the high bypass engine, where the air coming from the inlet, some of it is used in the combustion chamber to turn the turbofan, but most of the air that is created from the rotation of the turbofan, or from the fan, is pushed as thrust around the outside of the engine. So this high bypass ratio provides lower fuel consumption with the same amount of thrust. Now we're going to get into some of the specific engine components. So the first section of the engine is the intake, and the purpose of the intake is basically to direct airflow towards the compression section at a efficient angle of attack. It provides airflow for the fan and separates debris from intake. It also measures incoming air and temperature of the air. So some of the design characteristics of the air inlets. Um, so at some of they have like three different kinds. So the low speeds um, create some sort of air sucking condition where the air from the front of the inlet is being sucked into the engine. At subsonic speeds, a design is created to match the incoming airflow, so it doesn't need to create a suction in front. It just intakes all of the ambient air as it comes through the engine. And then at high speeds, some of the air will spill over the intake of the engine. So the convergent air section is sucked into the inlet and then diverges to slow the air down and create pressure in the inlets. Here you can see an inlet um, that is used to separate debris. As the debris and air comes in, the air can be sucked up through the intake section here, and the debris is heavy enough that it will fall through the kind of exhaust of the inlet here. So if there's any ice or rocks coming into the inlet, it will pass through without being sucked up into the engine. So now talking about the compressor section. There are different compressor sections, and it's basically used to increase the power output once it's burned. So as the compressor section compresses the air, it will become more dense and create higher thrust when ignited. There are three different types of compressors: the centrifugal, the axial, and the combination of the two. The centrifugal design of the compressor section is made up of three components. The impeller, which is the first component, moves the air outwards and directs it towards the diffuser. The diffuser then slows the airflow down creating a higher pressure in the system. And then the manifold will continue to move the air towards the combustion chamber. The advantages of the centrifugal design is it's simple to design and manufacture. Um, it's compact and a lot lighter than other designs and used for like smaller applications in aircraft. Some of the disadvantages or drawbacks to this is that there's a lower pressure ratio than the axial compressors and requires higher RPM to be more effective. Moving into the axial compressor. The axial compressor is composed of inlet guide vanes and then compressed with rotors and stators. So the advantages of the axial compressor is that these guide vanes are variable geometry guide vanes. So that this means that they can twist to guide the air into the compression section and limit any kind of compressor stalls that might happen. It then moves into the compressor rotors, which speed up the airflow, and then the stators will slow it down and compress it even further as it gets into the later stages. So this can be a multi-stage and multi-spool type compressor. The different factors affecting the amount of stages that are in a compressor could be uh, the number of compressor spools, the amount of energy extracted from the gas, the optimal RPM that they want engines to operate at, or the different aircraft space constraints that they might deal with. The advantages of the axial compressor allow for high flow rate of air coming into the engine, very high compression rates, which create a much more fuel efficiency. The disadvantages to this type of compressor is that it's very complex and expensive to design and manufacture and requires a lot more space due to the multiple stages. You can see the front fan blades direct the airflow into the low pressure compressor. And then they move into the high pressure compressor, the combustor, and the high pressure turbine and the low pressure turbine. So there's a lot of stages here, and that's why it's very fuel efficient, but also expensive and large. These can be used in turbofans, turbojets, turboprops, and most other gas turbines. Another thing to talk about is the use of bleed air. So bleed air can be high pressure air from multiple different stages of the engine. The higher stages of the engine will produce a lot hotter and more compressed air for the bleed air to be used. The bleed air is most commonly used with anti-ice pressurization for the AC units and for engine starting procedures. Another thing to bring up is how the engine speed control is governed since thrust can't necessarily be measured. So the use of fuel flow is monitored to control the shaft speed, um, and that correlates directly with the amount of thrust being produced. Now moving on into the combustion chamber. The combustion chamber's purpose is to mix the fuel and the air and ignite the fuel-air mixture, and it does not need to be reignited once it's lit. There are three different types of combustion, including the can type, the annular type, and the can annular type. So the can type is independent cans that are placed in a circle around the main spool of the rotor shaft. This design is more of the old style. It's kind of outdated and is kind of wasting a little bit of space, and you don't get quite an even distribution of combustion. The annular type is the newer, more improved version of this combustion. Um, so the annular type is composed of the nozzle design at the air inlets where the air is compressed, moves into the nozzles, which are combined with high fuel pressure mist. This donut-shaped design is allowing it to be connected all the way around the inner combustion chamber, so that the single flame can travel in a complete encompass circle around the combustion chamber. The annular type is a 25% weight reduction to the Cana type, so it's much more efficient. In this schematic here, you can see the inner combustion chamber is where most of the heat is being produced. And there are primary, intermediate dilution holes um, that mix with the outside cooler air. And this cool air helps keep the case from heating up the case liners too much. And this could be a problem if it gets too hot. Now moving into the exhaust section. The exhaust section is composed of nozzle slash turbine exhaust, which is monitoring the ITT or EGT. Combustion is used for turbine power to convert into rotational energy. ITT is the interstate turbine temperature, which measures the temperature between the turbine sections. And the EGT is the exhaust gas temperature, which is measured from the exhaust section. So you can see in these diagrams here, I included a nozzle that is restricting the airflow and then the exhaust nozzle, which is diverging the airflow. So the closed nozzle at the image on the top is going to maximize the amount of um, thrust and air away from the engine section. The open nozzle is going to increase the power at slow speeds to create maximum afterburn. This is basically the burning of any unburned fuel in the exhaust to create more power. Some of the design features in the exhaust section can be noise suppression, thrust vectoring, and the afterburner. So the noise suppression is basically reducing the temperature between the engine exhaust and the ambient air so that noise is not created. And thrust vectoring is the ability to change the direction of the exhaust nozzle to vector the aircraft. And this can be seen in the F-35 and the F-22. And then also, yeah, the afterburner I talked about with the exhaust nozzle being divergent. Next, we're going to be going into the operational considerations. So starting the engine is the first thing that we need to consider. Um, the most common way to start the engine is using an air turbine starter. Within the air turbine starter, pneumatic air is used to turn a smaller turbine connected to the accessory drive. This APU, auxiliary power unit, is used to create this air for the starter. If the APU is in op, hopper carts are used, so basically separate carts with hoses that you connect that will provide the pneumatic air to start the engine. If either of these are options, then you could use bleed air from the opposite engine. You just have to consider that you will have to leave the engine running if you do land and shut down one engine in order to start it back up. Also, electric start can be used. This is seen in the Boeing 787 and smaller gas turbine engines. The AC generators are the main energy source for the electrical system and can be the ground power system can be used if these AC generators are inoperative. Then we're going to be going into the abnormal procedures related to engine starting. First procedure is going to be hot starts. Hot starts are basically the rise of the internal turbine temperature or EGT in the start process above the limit that is recommended. This can be caused from the inadequate use mixture of fuel and air. This will result in the abortion of the start, and this can occur in higher density altitudes, maybe like Colorado. N2 stagnation is also known as the hung start. This is going to be the abnormal acceleration after the light off within the starting procedure, and the RPM is going to be below the normal idle RPM. To fix this stagnation, you are going to turn off the thrust levers and dry motor until the internal turbine temperature is reduced to normal. If you deal with no light off, this means that the fuel air mixture inside the engine is not ignited, and you won't see a rise in the ITT or EGT. This is most likely a failed igniter or pilot error that when the pilots forget to arm the igniters. And the last abnormal procedure is the no starter cutout. So this can be seen when the starter continues past the given time limit, and this occurs in more cold conditions or when using a huffer cart, which does not have enough air power. In order to correct this, you are just going to manually stop the start procedure. Another thing to talk about is fire monitoring and extinguishing fires in turbine engines. So the monitoring is by means of pneumatic sensing systems. Some of these are referred to as fire loops, like which are gas-filled pipes routed around potentially abnormal heat sources. If the temperature in the vicinity is sensing rises of the temperature, the electrical resistance of the core material decreases and a warning indication can be triggered. And to extinguish this, some aircraft have halogen on the newer ones that can extinguish fires when activated. Will extinguish the discharge into zone 1 of the engine fan assembly. Any fires in zone 2, which is like the engine core, are going to be extinguished by shutting down the engine, and the flight crew following the engine fire checklist, shutting down the fuel and the hydraulic fluids, and monitoring the oil supply or potentially any other flammable substance on an aircraft. Going into specific gas turbine engines, I'm going to be talking about the Rolls-Royce Trent 700. Overview of this engine, it is a high bypass turbofan, meaning it's going to be more fuel efficient using these exhaust gases to turn the fan and create thrust. It is axial flow. It's originated from the UK, and the 1 unit price for this engine is $23.25 million. This can be seen or used in the Airbus A330 or Airbus Beluga XL. And so the components of this is that same of the turbofan schematic. Compressor composed of 26 wide chord blades, 4-stage low pressure turbine, then 8-stage intermediate pressure compressor, the 6-stage high pressure compressor, and the combustors are the annular combustors with 24 spray nozzles. The turbine section is composed of single-stage high pressure, single-stage intermediate pressure, and 4-stage low pressure turbine with a 5-to-1 bypass ratio. The performance of this engine is 67,500 to 71,100 foot-pound of thrust, and using full authority digital engine control. And here is the works cited. Thank you for watching.